Hi everyone, in this video I'd like to introduce this exactness corollary. It's about the differential equations in differential form. So it looks something like this. M and N are two variable functions with the condition being continuous and its partial derivatives, both for x and y, are continuous. Actually, the both partials is not necessary, but it's easy to say, so that's how they phrase it. This theorem, concerns that we're given these two variable functions. Can we realize those m and n as a partials of a single functions? And it says if we have the following condition: partials of m with respect to y, partials of n with respect to x. If these two things are equal to each other, then there will be a function f of xy only locally, such that its partial of capital F realizes m and n like that. The main purpose of this video is twofold: to connect this theorem to something you have seen in Calc 3, vector field context, remind you a little bit of that, and go to the differential equations in differential form. So in the differential equation context, the differential equations that satisfy this condition is called exact. That's why it's called exact. The reason it's corollary, I call it corollary, is that it's actually coming from the bigger context than just the differential equations. So that's kind of follows from Green's theorem in the context in the calculus 3. Right here in Calc 3 we introduce something called the vector fields. The examples of the vector fields were force field and velocity fields, and whatever the information that requires not just a scalar and direction and stuff like that. That's called vector fields. And this capital F is any this any one variable, two variable scalar function. So its input takes two variable, but its output, capital F, is a scalar. So it's a scalar valued two variable functions. And this symbol is called gradient symbol. So if this one denotes that if you're given scalar valued two variable function, you can create a vector field using its values of a partial. So this whole thing is called a gradient vector field. This is usually introduced at the beginning of the multivariable calculus as the direction where the rate of change is maximized. Rate of change of the value of f is maximized. That's usually how it's introduced. Then there is this important question: is if there's an arbitrary vector field is given, can that be realized as a gradient vector of some function, scalar valued functions? In the physics context, this scalar valued function f is called a potential energy function, and this is by doing this process you can obtain the vector field that it actually in practice, but it's more packed information. You're going backward a little bit. That's the potential function f, and the condition was that this thing we call the curl in the calculus 3, it's more complicated than that, but just for this two-dimensional vector we can simplify the curl to be this scalar, so which is exactly the condition I showed in the exact statement of the exactness corollary. So in that is equivalent, that curl here is being 0. But even if it is a three-component vector field, and therefore you have a gradient vector that's three-component, this formulation is the same. The formula of the curl is slightly more complicated. The vector field is given, and there's curl vector field. So this is the important statement you might have encountered in Calc 3, but sometimes it's not formulated like this. So there's an operator on the vector field, which in general gives you another vector field. If that curl of this given vector field is a zero vector, then it implies the given vector field here is a gradient vector of some potential function, gradient vector field of scalar function. But this only works locally. Only locally like this. If you try to find this function capital F in a really big range, you might get into some sort of problem. And this difficulty of to define this function in a large domain is demonstrated in my series of video in my Calculus 3 playlist of YouTube. Find those videos titled Stokes' Theorem and Divergence Theorem and so on. But locally, you don't have to go through that topological situation. And locally, it's very accessible. So that's what we are looking at here. And especially in differential equation, we are only concerned with the local solution sets. This typical context of initial value theorem. So this will be a very accessible statement. That's exactly more general context, the statement of the exactness corollary I showed earlier. So we are back in the context of the differential equations. So this is slightly more general than just a function of y of x. It was we started with a Cartesian equation where there is no derivative in here. It's just the Cartesian coordinate x and y set equal to 0. Often we have this explicit version, which is elementary expressions in x and y. Yet it defines this type of a graph, and if you look at locally around it here, it defines implicitly defines a function. And often we don't have elementary expressions to describe this function here and there, but it certainly locally defines a function. So we take that as the exact form, a form of a function. So rather than looking at y equals yx, if you parameterize this graph given by this Cartesian equation, it's better to handle this differential equations in differential form. So we write it like this: x is xt and y is yt, a parameterization. And this vector dx dt and dy dt, the derivative of this thing, form this tangent vector. In Calc 3 and physics, this is called the velocity vectors. And this is, again, a Cartesian equation. There's no derivative, and here's how we pull out a derivative out of it. We differentiate this one with respect to t. That's the key here. Not with respect to x, not with respect to y. We're doing this with respect to t. Then this is two variable function further composed with one variable. So we go through the chain rule, and these things I explained in my earlier videos. And that's the partial derivative of f multiplied by dx dt. So rather than writing all dx dt, we understand the main variable is t here. So we abbreviate like this, and this differential equation is called differential equation in differential form. You might learn this in the Calc 3. This thing is just two quantity multiplied and two quantity multiplied, and after that is added together. But if you're still fresh with the Calc 3, this is called a dot product. Sum of the product of numbers can be turned into a dot product of two vectors. So one of the vectors this, that is a component from this vector, velocity vector. Whatever the other two components makes it, it's going to be a vector, but the left-hand side is the dot product of that vector and the other vector with this component, and dot product 0. And if you remember dot product 0, that is a perpendicularity in this two-dimensional world. So whatever that vector, the remaining two factors is, that is the vector that is perpendicular to this dx dt dy dt, that's kind of tangent to the curve and the velocity vector. That must be 90 degrees. So either is in that direction, is in that direction. So that might ring a bell. So that's of that importance. Not only just pops out of the chain rule, which I also explain why things work like that in my earlier video, it has this significance to the geometry of this curve. So this is a curve and kind of tangent. And the direction of which way it goes is determined by the levels. This is level 0 when f equals 0. You can imagine whether f equals 1 is, either outside in this side or that side. So for example, f equals 1 not equals 0. F equals 1 is over here, and this is the way the arrow goes. The direction it maximizes rate of change, so there must be increasing direction, so that determines it. So that's the significance of this one, that's just a chain rule. And this is the connection to the exactness theorem. This is kind of motivation for another review from Calc 3, I think. M differentiated my, that was a part of the curl condition. So you know this part is going to be m, that part is going to be n. So if you differentiate this m with respect to y, that would be, this one already had a derivative x first, and this is operator. It's usually operator is written to the left of the earlier operation done, so it's written like this. The other part of the condition is n here differentiated with respect to x, but n itself is a derivative of fy, so differentiation later. So this comparison of my and nx here is really the same two-variable function differentiated with respect to x first, y later, versus y first, x later. So is this two things equal to each other always? That is something called Clairaut's theorem. So if f and this two-variable function capital F has a continuous partial, second partial I think, then these two are necessarily equal to each other. So that's an interesting theorem, and I have a video as to why this is true. If you think about it, it's especially if you look at the pictures of the graphs of this two-variable function, it's absolutely unclear why these two things have to be equal to each other. But that's Clairaut's theorem, and a further explanation in Clairaut's theorem is available under this title Clairaut's theorem in my playlist, the Calculus 3 lectures. But if you compare this statement here with our statement, it's kind of converse. We started with a Cartesian equation. If you differentiate it, it satisfies the condition in the exactness theorem. But the exactness theorem says we don't know if there's this function that gives you the differential equation, but we only know these two things are equal to each other. Then the exactness corollary allows us to conclude if these two things are equal to each other, there is actually this two variable scalar valued function f set equal to 0. So that's this statement. Okay, so we conclude there is this f there in this corollary. But Clairaut's theorem starts with an f and show this is satisfied, so it's a back and forth. So this converse of this one is also true. So from here will be a proof to the exactness corollary, and I will skip some of the fundamental part and push it into the second part of the video, but this proof of this part is some general formulation of how you actually find that f in practice. Often you probably practice by now that how to find that f in practice, so this is kind of general formulation. It's still neat in how these things operations are played out. And of course, when you read the proof, and you have to pay attention to how the hypothesis kicked in and helps us to discuss this and allows us to move on to the next part in general. So that's always things that you have to pay attention to when you read a proof. Often student expects that proof shows you how to discover the answer, but often mathematicians just sometimes explain, sometimes don't. They don't. If they think checking procedure actually reveals pretty much the process of discovery. So I follow that because I believe when we check our candidate in that process, it kind of shows you how things are discovered. But if you go through the discovery process first, sometimes could be confusing and stuff like that. So the proof only had to contain the validity of this development, rigorous development, not necessarily have to explain motivation. So if you think about the statement, it asserts the existence of this two-variable scalar valued function. So usually proof of that kind of statement goes, you go ahead and force to define it. Doesn't matter how you find it, you have to give very clear definition with no confusing and ambiguity part. I give you x and y. What is your function? How do you define it? You have to give that first. The next thing you have to check is that the function is defined in a clear fashion like this. Does that satisfy the property that is exerted there? So let me show you the statement again. So here's the statement: m and n are given and they satisfy this condition. Then we have to construct this f, then show that its partial derivative matches this m and n. So we're in this process of defining it. But at least I'd like to mention a little bit about the motivation behind that. How we're defining this function f is the following thing. If you're asked, actually, if you're given m and n, if you're actually asked to compute what this f is, the first thing you do is that you look at this m, coefficient of x, dx part in the differential equation, and integrate it with respect to x. And then you throw in the part that only depends on y, because this one differentiated with respect to x is definitely just m, no matter what this one is, with as long as this is in y. So that's our candidate, and then you differentiate this part with respect to y, that part with respect to y, and compare that one with n, and figure out what this one has to be. That's usually how it goes. So the following definition is motivated by this process, so you will see this one shows up. And then I did the calculation, this process, and realized that the candidate of the field y has to be in that shape, so I'm going to throw that in, part of the definition of capital F, and just show those two partial condition matches with this definition. Like I said, it involves integration, and here this is indefinite integral. When you write a proof, you try to get rid of as much as ambiguity as possible, anything that is uncertain. Then if the readers and the writers in a certain level, and that's allowed, but it's best always to, when you define something, you define it clearly, really clearly, and that's the best way to write a proof. So it's locally, so we have to based on some things, for example, a comma b, x value, and y value b, and around it we are guaranteed that this two variable function m and n are well defined around it. Maybe this is the region around it is well defined. The nature of the integration along the x and along the y, it's beneficial to have just little rectangular boxes around, so that correspond to integrating with respect to x. Then it's you want some values around here horizontally. If you're integrating with respect to y first, then you want some values around here, which is eventually what we do. So we need to have a guarantee to have some rectangular box around a comma b, the function here mn, such that we can go through the integral process. And even that integral process is not going to be just indefinite, something definite, so that it is set in stone. It's a very clear definition. So instead of this, we're going to use definite integral. So I did this calculation ahead and thought about what should be this phi y should be clearly defined, and it turns out it's integral of n with this a, put it into x slot, and integrate this y from b to the y slot here from b to y, where y is given x and y. So given x and y, how are we going to define this capital F of x, y? Bits and this bit here must be defined like this. So when I'm checking, you can clearly see where I got this from, but you can, you can kind of get rid of b and y and think of it easily. Okay, that's the integral of n. But you can see everything specific here. This is as long as this ab is given, and this is clear definition. And finally, here's a definition of f. This integral part, integral of m, should be y part's fixed. So this starts from a comma y, and y is fixed, and that is exactly this value. I give you 3 and 2. That's happened to be close to this a comma b. Then this is going to be that 2 that I put in the y coordinate for this capital F. So this is the integral. along x slot. The beginning value is a and terminal value is that x. So that's this part. And as a definite integral, and phi y is exactly this one. So that's our definition. And you have to take a moment, see if there's anything is unclear. If I give you these two value, and you put that number in, a is given, y value is exactly that, so this integral makes sense. And that one we already discussed, this integral that makes sense. And here's where we need to mention the one of the properties used. The continuity of these n and m as a two-variable function allows this m, where y is fixed as a function of u, is still continuous, and that function where x part here is fixed as a and looking as a one-variable function in the second slot, that becomes continuous. So the continuity of one variable function in this one variable integral guaranteed to exist. So that's the integrability of continuous function. So that's where the continuity is used. And then I wrote this copy in here, that phi y part in more explicit form here. So that's our definition of f of xy. This is usual thing, go through the integration of m, more specifically like this. We've seen that in the initial value problem technique. And the remaining part that only depends on y must be in that form, I realized. So, however I got this one, the remaining part is you can define anything you want. F of xy could be anything. They just make sure in the rest of the part, what you got here is the correct one by checking that property. Now here's f, the definition of f. Now I'm checking that does this one really have a derivative, partial derivative of x being exactly equal to m? This part will be easy because that was exactly the opposite procedure that is involved in this definition of f. So I'm going to put that symbol in here and there and see what we get. So the differential operator, partial differential operator, applied it here and linearly applied it there, and that's how it's differentiated. And this part, and as I wrote it here, emphasizing there's no x involved in here, this is only in terms of y, so partial x will give you 0, so that's gone. This part is although it's a partial, if you look at here, it's really one variable derivative, and where y is fixed. So differentiated, this is the area function from constant to the solid x. There's no other complicated variation of x in there. That's exactly the fundamental theorem of calculus. This area function, if you differentiate it, that becomes exactly inside function where the dummy variable is replaced by x. That's fundamental theorem calculus. So that's this part right here, and that part's a 0. So the function we defined here has a partial x exactly m. So that satisfied it. First condition, and of course the second part is where other conditions kick in and make this second part satisfied. So let me remind you of the definition before we hit this y, because it's not showing. Here it's our definition in integral form, and we're about to hit this partial derivative both sides with respect to y. So here it is, that is applied to both part. And this is fundamental theorem calculus again. If you look at it here, that x slot is constant. We're only doing with respect to this part, and y is the variable, and we're differentiating with respect to y. So that's fundamental theorem calculus for one variable. So because of that, this whole thing is just simply this inside function where u, the variable part for the integral, is replaced by y. So that's that. And this part is interesting part. It's usually I phrase it as a different order of operation. We go through integral first and differential operator later, but this variable y and that is not the same. So fundamental theorem calculus does not apply here. But we're wondering, if this is integral first and differentiation later by different variables, can we actually do that? Derivative inside first and integral later, that will be a different order of operation. Here, because the variable is the same, this actually cancels. And here is different we're asking, can we swap this to symbols? You probably know many examples. The order of operation makes a difference, so you can't just do that. You have to think about whether it's allowed. So that is where this continuous partial technique conditions used to allow this thing to happen. So I justified this process in the part 2 videos, and here I'm just saying that the continuous partial condition was used to swap this one and to guarantee that easily that differentiating first and integrating later is going to be equal and to the earlier quantity here, and that was just copied here. Okay, so look at a part 2 video to see the details of this part. Don't be disappointed, it's still very interesting. Even with that part, there's something interesting part kicks in and makes you probably curious that what this curl condition is really about. So we swap that, and you look at this partial of m with respect to y, and that was the part of the condition we have. If you have my, you can switch to nx. That's what we have there. This my, the whole thing, can be replaced by nx because they're equal to each other. That's a part of the condition. Now once you do that, you can see that this variable x switch makes these two things equal to each other. So that's nice, and an x there. This part is that when you evaluate the definite integral, you want antiderivative of inside function, but inside function is derivative of something, so you can see that n is the antiderivative of this whole thing, right? If this part's confusing, you can write down an example. Derivative of something, what could be the antiderivative? The function before you differentiate it. That's the answer, right? So there's your n. That's your antiderivative. One antiderivative helps us to calculate this definite integral. So there's your antiderivative for that inside function, and evaluate x and a. So that gives you, plug in x in here, that's xy, a in there, that's ay, negative. And this is exactly how I got this nay after you differentiate it, so that these two cancels, and it just leaves nxy, which is what we wanted. So I looked at this part first and think about what to put in here so that they cancel out, and have to just integrate, go back to the formulation. And this is the result we wanted. The derivative of capital F with respect to y being the n. So the construction of our f has the property satisfied. So here's a summary. We defined the function capital F of xy in this way, given m and n, and this local point a comma b, we constructed like this, and we were able to show both partial derivative matches this condition. And all of this thing happens very close neighbor, guarantee that there's at least a small region around a comma b, so we can do that. So if you think about how to do this one in a bigger area, and first this one is, let me show you the picture. So here's the picture. This integral requires you start with initial point A, and your y coordinate is b, so it's kind of, a comma b, so a comma y could be somewhere here. Then you're integrating that, and you're plugging in u comma y, so y is here. U can be any range between a and x, so a starts here, it could be over here. So to do this process, you guarantee to have no problem along this horizontal line. And to do that, and at a we must have no problem with going up and down. But if you do this too long like this, you might bump into some sort of problem where maybe over here m is not defined, something like that. So that's the problem. If you can maneuver around like this, doing this, jiggly stuff, and yes, you can continue this process. But this simple definition is not going to be easily extended because of the undefined region of m and n. But at least locally, not in a big sense, locally we were able to construct that function, so that's the proof. If you want the detailed discussion of why the continuous partial allows us to swap this integral and the differential operator. See the part 2.